Hi Jaydeep, it's the sound okay?
Yes,
Okay,
sounds fine.
we're about to start now. Ready? Yeah. Okay, welcome everyone for our another episode on FSI Seminar Series. Today we have Dr. Tarek Saab from University of Florida to tell a little bit about our speaker today. He has been involved in dark matter searches for over 20 years as part of SuperCDMS collaboration. He obtained his PhD in 2002 from Stanford University and followed that by a postdoctoral fellowship at NASA Goddard Space Flight Center, where he applied the dark matter sensor technology for use as high resolution X-ray microcalorimeters that are intended for observatory missions. Since the joining of University of Florida in 2005, he has resumed his focus on the dark matters, direct detection searches, and currently serves as the SuperCDMS collaboration spokesperson. Thank you for doing the driving, and thank you for being available today. Please, time is yours.
All right. Well, I appreciate the opportunity to come visit here and talk to you about the experiment I'm working on. So my goal today is kind of give you a picture of how we go about searching for dark matter in general, and then sort of I'll dive into the specifics of the SuperCDMS experiment and how how we're going around doing that. This is the actual slide here. All right, so I'm gonna start very briefly with the how do we look for dark matter, and I'll start actually from the point of assuming we understand the evidence that supports the case for dark matter. So usually with these kind of talks, you spend 15-20 minutes kind of justifying what is the observational evidence that suggests dark matter. I'm going to actually focus not on the why there's dark matter, but on the how we do it. I'll just say that this is, up until this point in time, purely astrophysical based measurements, kind of from the scale of individual galaxy rotation curves, from the scale of galaxy cluster, the motion of clusters, from gravitational lensing, and even at sort of cosmological size, the expansion of the universe as measured by supernova, come together to have us form a model. It's called the called dark matter model of cosmology, where 70% of the mass energy density of the universe is in the form of something that is basically an expansive pressure, sort of something like a cosmological constant or an energy field. And then 30% of it is in the form of something that's gravitationally attractive, which basically means matter, mass, as we typically understand it. And now of that, only 5% is what we normally associate as regular matter, baryons and electrons, protons, everything that's made up of quarks and electrons. And that is explained at the particle level by the standard model. So we understand how these particles interact. We believe that this, 5 times more in terms of mass of something that has to be a particle, but it cannot be one of the particles that we know so far. So it cannot be made out of the standard known quarks or the standard known leptons like electrons. Otherwise, the interaction between these two kinds of species would have led to very different observational sort of phenomena than we've seen so far. So then the question becomes, okay, if this type of particle out there that interacts very, very, very infrequently with regular matter, how do we go about looking for it? And there are a couple of ways. We can kind of divide dark matter searches into 2 categories. One is we call indirect searches, and those you're looking for the end product of dark matter interaction with other dark matter particles or other particles in the galaxy. So wherever you have regions with high density where these particles kind of accumulate, namely at the center of the galaxies or towards the center of the solar system or stuff like that, we have big gravitational wells. there's a chance that these particles will encounter each other. They'll undergo some, interaction process, some annihilation or other physical process, and they'll emit standard model particles like, say, high energy gamma rays or electrons, positrons, things that we may be able to observe on Earth or via our instruments. That's indirect search. What I'm involved in is sort of the other category, which is direct searches, namely if dark matter is your honest to goodness just regular particle, and there is a chance that it'll interact with baryons, with protons or atoms, then we're looking for this type of interaction, a simple elastic scatter. And the reason we look for simple elastic scatters is because if you consider the energy of dark matter particles that are trapped in the galaxy at our location of the galaxy, right? For them to be gravitationally bound at our location, that gives them a maximum amount of kinetic energy they can have on the order of a few hundred kilometers per second. And so at the particle level, that kind of kinetic energy is predominantly only going to give you elastic scattering interactions.
What's the force?
Unknown, whatever that force may be. So yes, people have considered the most likely cause of the force to be something that originates from supersymmetry. That is now has been disfavored. So they're looking, you might hear, like if you listen to sort of the particle physics talk, something called dark sectors or things like that, which just means I postulate a new force with some sort of interaction between that particle and the standard model particle. And so it's you quantify it by some scale, some number. But the speed or the kinetic energy of the dark matter particles involved will still end up giving you a fairly low energy, a fairly elastic interaction. So it's a general scope of models. I don't want to say that's true for anything that you can postulate as a candidate, but for most theories being studied, this is the interaction that happens.
And you also make the assumption that that force is much larger than the gravitational interaction between those two particles. Is that correct? Because the chi and the target should gravitationally interact.
Yes, so they do gravitational interact. If so, I'll put it another way. The magnitude of that force gives you the interaction probability of that particle with regular matter. And yes, I think it has to be on a much higher scale than gravity to actually start seeing interaction. But that is an unknown quantity and something that we try to measure in a sense with these experiments. Absolutely. Yeah.
This dark matter is some kind of cold. It's not very energetic.
Right. Yeah, and this is actually the energy speed, the energy scale involved. This is kind of on the order of a few hundred kilometers per second. At 500 kilometers per second, you're already beyond the escape velocity at this location. And so these are very much non-relativistic particles. Absolutely. Yeah. So if you were to do kind of a simple, again, physics calculation of if you have all particles coming in with a single known velocity and they can interact elastically scattering off of an atom, what you see is if you measure the energy imparted to the atom is a distribution that's kind of flat, that goes all the way from 0 up to the maximum energy that this can convey, which depends both on its velocity and its mass. And then you can't have it impart any more kinetic energy like that. So that is a good kind of spectrum, because if you measure something like this, then you actually know something very clear about the dark matter particle. You can basically determine its mass. Unfortunately, we have very good reason to suspect that dark matter don't all move around the galaxy with one speed. So you kind of add the next level of complexity is you say, okay, well, let's say they have some actual speed velocity distribution. And the simplest distribution we can posit is a thermal distribution. So this is just a Maxwell-Boltzmann velocity distribution, which may or may not be, again, totally appropriate. There's, again, people that said dark matter should not have had time to thermalize, in the galaxy, so it could be something else. But at least this is some sort of distribution centered around, a few hundred kilometers per second. And so then this is what you would expect to see in the detector. And again, this is a log scale. So it's falling very fast. In other words, most of the interactions that you see are on the low energy scale of things, which And this x-axis is on the order of keV of energy. The magnitude of energies involved depends very much on what kind of area you're searching in, the kind of physics you're doing. If I talk to my colleagues at CMS and I mention keV to them, they don't even know what that is. If it's not TeV, it's, it doesn't matter. But on the other hand, people involved in X-ray astrophysics and sort of the like, this is the energy scale that sort of they live and breathe in all the time. And then, so of course, there are lots of interesting phenomena that happens at lower energies. But in terms of particle detectors, keV is actually a fairly challenging regime. And again, the last thing I want to show you is if we do add that cutoff velocity, the escape velocity, then that just serves to push the spectrum even lower. All right, so this is, I think, maybe one or two equations I'll include today that kind of show you how we can calculate the previous curve. There's nothing magical about it, but it's interesting to look at because it sort of brings in three elements that we're trying to understand. One is it brings in an element from particle theory. So again, you have to go to a model and say, okay, what do I think the dark matter particle could be like? What is the type of interaction? And that predicts a certain cross-section, or a cross-section that scales with some parameter in your theory, and sort of a mass range that you're searching for. And then this term here is a function that actually describes your target material, your target atom, because the assumption is at those speeds, at those interactions, because they're elastic scatters, low energy, the particle is interacting coherently with the whole atom. And so this is just a function that encodes that. And as you go to higher and higher energies, you start to lose coherence and this drops off. And then finally, there is a term that basically that tells us about the astrophysical properties of the dark matter distribution. So what is its velocity distribution? What is its local density where we are here on Earth or wherever you happen to put your detector? And so all of these three terms go together to produce basically the interaction rate that you would expect to see in your detector as a function of energy, differential interaction. So again, this is the same function that I showed you before. If you build a particle detector and you operate it for a certain amount of time and you see an energy spectrum that looks like this, you can say, great, this is a sign of dark matter interaction. Except if you do that, that's not what you're actually going to see. You're probably going to see something that looks like this. Because when you build a particle detector to detect dark matter, you're not just going to detect dark matter. You're going to detect every other kind of particle that comes your way. And there's a lot more of basically background undesired interactions than there are of dark matter interactions. Otherwise, we've discovered it already. And so most of the challenge with dark matter searches is really learning how to get rid of background. And this is part of the reason I'll show you, later in the talk, these experiments actually have to be performed underground, because where we are right now on the surface is a highly radioactive environment if you're interested in doing sort of rare event searches, just cosmic rays from the skies surrounded by natural radioactivity and all the elements that surround us will overwhelm these kind of searches. So this is a diagram. It's a messy diagram, I know, but it kind of helps us quantify what's going on. This is a simulation of what the SuperCDMS experiment might see once we're operating. So I'll kind of point out a few features. So in pink are the potential spectra that you would see for various dark matter candidates as a function of mass. So the lightest candidates would give you the steepest, the lowest energy kind of spectrum. Most of the events are down here. And then as you go up in energy, there's you'll be able to extend the spectrum, but of course the overall rate comes down. And then the other various colored curves are our estimate of what the various background contributions are. So in red are gammas that are again coming from the surroundings of the lab of the cryostat, and green are electrons, again, just standard radioactive emission. We try our best to build the experiment out of the most radio pure material. We the whole challenge in this is to make it as clean as possible, but this is what as clean as possible is right now. That's the state of the art. So the y-axis tells you kind of, I said that already, the rate of events that you'll see. So if like this number here is 1 event per kilogram per day of detector. So, and detectors are on the order of 0.5 kilogram or so. So in other words, the rate of interaction is on the order of, this is a couple orders of magnitude below. You might see a handful of dark matter particles per kilogram per year of operation, whereas backgrounds occur at a much, much higher rate. The cyan line, I should point out, is neutrinos. So the same way you can have regular particles, photons interact with detectors, neutrinos also will interact with atoms at a very, very small cross section. But again, we're looking for events that happen so rarely that, in a given year of operation where we might see, or look for dark matter particles, we do expect to see on the order of a dozen or so neutrino events in these detectors. So that sets the scale of the rarity of these interactions.
Neutrino flux is larger than a neutron flux? Is that the reason the rate is?
Well, yes, the neutrino flux is huge. Absolutely. So even though the cross section for any individual event is ridiculously small, together they give you a finite. Overall.
Where is the neutrons coming from?
The neutrons are primarily coming from rock. So there are 2 channels for producing neutrons. One is just the natural abundance of uranium and thorium and their decay products will produce neutrons. The other source, which is the also really pernicious source, is cosmic ray muons will go through material, will go through nuclei, causing them to fission and will emit high energy neutrons. And that's part of the reason actually this experiment or this whole class of experiments have to be deep underground, is because it's the only way you can sort of get away from the muons at the surface. You just have to have the Earth attenuate them for you.
But underground cannot filter neutrinos.
No, they cannot filter neutrinos. That's an ultimately irreducible background. Yeah. There are things we can do about that. Actually, I'll sort of touch on it in this next slide a bit. The neutrinos are, in a sense, a known quantity. So even though you can see them, as long as you have a neutrino spectrum that is distinct from a dark matter spectrum, you can still search. You run into a problem when, for certain mass ranges, actually the spectra look similar, and then you can't tell one from the other. So what is it that you get when you actually build and operate a dark matter experiment? And we are really sensitive to 2 parameters of the particle, namely the interaction cross-section, right? That's proportional to how many events you see in your experiment. And then the mass of the dark matter particle, because that comes from the shape of the spectrum, how steep or how flat it is. And so if we're, for the many decades that these kind of experiments have been operating, the main result, if you want to present it in the paper, that kind of is called an exclusion plot that is in a, plotting cross-section versus mass. What if you run an experiment and you don't see any events that are consistent with dark matter, what you're able to say is any theoretical models that predict a cross-section higher than this line are ruled out, because otherwise you'd have seen more events in your experiment. And any models below that line, you cannot say anything about simply because you don't have collected enough data or the background is too much. So that's called the exclusion plot. And I don't have any numbers on it here for a reason, because for many years, papers will come out. If you take out the numbers, they look exactly the same. No experiment has claimed the signal yet. There's always a theoretical region that's favored that's just below your reach. And 5 years later, you build a better experiment and you push down and you still haven't seen it. But then the theorists realize they forgot a factor of 2. And so their models kind of move down a bit. But, so it's a little bit of a cat and mouse game. For a long period, we actually had a very, very good theoretical target that comes from supersymmetry, because supersymmetry gives you very specific predictions and actually would have resulted in high interaction cross sections that would have been seen by now. But based on these type of experiments and based on what's seen in the colliders, supersymmetry is not a very favored sort of model right now. Anyway, so over time, you keep going down, everything looks the same, but then, like as of the last few years, a new feature kind of starts appearing in these plots, which is neutrinos that I mentioned. At some point, the experiments are so sensitive that you'll start seeing neutrino events. And below a certain cross-section, so this sort of the pink line represents the equivalent dark matter cross-section for which you'll start seeing too many neutrinos in your experiment to kind of really make a claim on the dark matter. So it's not really a hard limit, but it just makes your ability to search deeper, for more rare interactions much more challenging. Because most kind of background we know how to mitigate. Not saying it's easy, but at least there's a known, path. Neutrinos, you have to live with them. There's no way to get rid of them. And so this kind of spurred, actually, along with the fact that supersymmetry does not seem to be kind of the next valid extension of particle physics. But people say, well, okay, why are we looking in this region of high mass? And to give you something more quantified, this is mass scale on the order of 10 GeV, so the mass of a proton-ish, or sort of light atoms. And then theorists kind of said, well, what if we look at models that have actually much lighter candidates? What can we say? And they realized that there's really that parameter space is to a large degree unconstrained, and there's no reason not to look there, right? And so the last, actually 2 years ago, there was sort of a big field studies called SNOMAS, where we had theorists and experimentalists and everyone come together and say, okay, well, what is the big next step we have to take if we want to actually pursue the idea of detecting dark matter? And well, a lot of papers came out of this, but sort of this is like the summary slide. So this is the same kind of diagram I showed you before, but now with actual numbers on the X and Y axis. So for the longest time, the dark matter searches guided by supersymmetry were looking in the range of 10 GeV and above, and sort of this beige area is the region of parameter space that has already been ruled out. In the green area, sort of that's labeled operating, these are experiments that are actually ongoing right now or in construction. Sort of they expect to be able to carve this this region parameter space, and then there are ideas of what to do next. And it might be hard for you to see on this one, it's a bit faint. There's sort of this line here with the gray fog, with the gray line that's called neutrino fog. As you can see that the experiments will start to enter the region where neutrinos are a distinct background, and just have to deal with that challenge. And then new technology, I interpret that as something like magic. Somehow we'll discover something new that will allow us to these searches. But so some people are more optimistic than others. I'm the pessimistic end. This, by the way, 10 years ago, the same sort of process happened, and it shows you the rate at which the field is advanced per decade. So it's, the field is always advancing, but parameter space, if you ask a theorist, is very huge. So imagine if you are able to go down from here to here in 10 years, maybe another 10 years will give you a sort of a similar improvement. Let's take this figure, and actually in the same paper, people say, well, why are we constraining ourselves to a certain class of theories or certain class of models? Let's throw everything against the wall and see what's even possible. And so this figure that I showed you before fits in an even larger range. I mean, these are not as well studied or understood, but there are valid ideas out there. And so it gives you the idea that searching for dark matter, again, 10 years allows us to probe this little region here. You're truly looking for a needle in a haystack. Supersymmetry was great because it gave us a goal. Everyone knew where to look, and then you can design an experiment and build an experiment for that specific goal. But when what you're looking for is not as well defined, you don't know how to build an experiment that's going to look for dark matter over here operates on very different principles than something that looks for more massive stuff. So it just kind of makes us take a a step back and sort of appreciate that this is a kind of a challenging problem. All right. Having said all that, at some point, you just have to build an experiment and look wherever it is you can look. So now I will tell you a little bit about the SuperCDMS experiment and sort of the technology that we use. The idea behind dark matter detection, or really the particle detection, it's a generic particle detector, is fairly straightforward. Imagine you have a chunk of semiconductor. So in CDMS, we use either silicon or both silicon and germanium. And we can apply a small or some sort of electric field across it. And then you ask yourself, what happens when a particle comes in and interacts with a nucleus? So this is generic, by the way. It could be any particle. As if you give a silicon nucleus a knock, 10 keV of kinetic energy, what is going to happen? So there are a couple of processes that take place. Because this is a semiconductor, you are going to create a population of electrons and holes right away, right? So you have the recoiling nucleus will have enough energy to excite electrons and holes. We apply an electric field across it, and then you can measure that. At the same time, because you're in a solid material, the recoiling nucleus will create a population of phonons. And those phonons will bounce around and they eventually will reach a surface where they can be absorbed. And so both of these techniques, you can give you independent measurement of the energy that got deposited in the detector. Now the question is, why do you want to measure the same thing twice? And the nice thing about doing it this way is the phonon channel is purely dependent on the recoil energy of the atom. So it just measures the total energy that you imparted to your atom. It doesn't matter what kind of particle there was. The electrical channel, the electrons and holes, the amount that you produce is proportional to the energy you deposit, but some particles are more efficient at producing ionization than others. And so you'll get a larger signal if the incoming particle was, say, a photon or a muon or an electron, anything that interacts electromagnetically, rather than, say, a neutron or a dark matter particle. And by measuring those two signals, you can identify and kind of reject at the data analysis stage the vast majority of events that come from unwanted backgrounds. How do you actually measure the event that happens? So in the animation I showed you, phonons are bouncing around. They are carrying energy with them. They are absorbed at the surface in a thin layer that's called a transition sensor. It's, in our case, we make it out of tungsten, but it could be any superconducting material. If you arrange it to sit right in the middle of its transition, any small amount of energy deposit will give you a significant temperature change. And so if we measure current and small temperature change, resistance change will give you a big current change and you will see a pulse. And that pulse is proportional to, I'm just going to kill that weird thing, to the energy of the event. Oh, we get to see the animations again. Sorry about that. Yeah. So that is the idea of how these devices work as particle detectors. So they not just count the individual interactions that happen, but give you a measure of the energy that's deposited as well. And at the same time, you measure the electric signal sort of by observing the voltage over here. There's one other thing that happens actually as the electrons and holes are moving in the crystal, under the influence of the electric field, they're being accelerated, right? So work is being done on them. The work kind of then gets, that energy gets redeposited in the crystal in terms of phonons that are emitted along the way. This is the equivalent of, friction is not really the right word, but the fact that you're dragging these charged particles at constant speed through the material, the energy they're gaining from the field gets re-emitted as phonons. The useful thing about that is it actually means that by cranking up the voltage here, you can increase the amount of energy that gets created, and that gives you a way of amplifying the event. Why do we care about that? Earlier, I was showing you that in the theories were kind of now suggesting dark matter might be a lower mass, which means the energy that it would deposit would be even lower in your detector. And by using this approach, you can amplify the signal into something that's measurable. It allows you to look for the lowest mass scales possible. So it's kind of a little technique that extends the mass range of the detectors. So anyways, this is the idea. You measure the total energy in the phonon system that is going to be dependent on how much energy the dark matter particle gave. So this is really the physical quantity that you're after, and then how much ionization is produced. And knowing these two quantities, you can back up the physical the quantity that you're interested in. All right. One side effect of this is actually, it turns out, these detectors can be very, very sensitive charge counters. So here, with a high enough resolution, right, the phonon signal depends on how much electron holes created and the applied voltage. So if you have a specific sensor resolution that says, okay, I can measure it to plus or minus 100 dB or something, by cranking up the voltage, you're effectively lowering the threshold or improving the resolution. What we see here is one of these devices where we shine the laser on it, and we're able to observe events with integer electron hole pairs that get created. So 1, 2, 3, 4. So you can actually see events and count how many electrons were created this event. And this gives you an effective resolution on the order of a few percent of a single electron. This is what the detectors themselves look like. As I said, they're made out of silicon or germanium. They're on the order of kilogram scale. So these are 4-inch diameter by 1-inch thick crystals. You want them ideally to be as big as possible, because to give you more mass, more atoms for dark matter to interact with. But also you have to cool them to 15 millikelvin. So it is a cryogenic device. Why that cold? Well, as I mentioned earlier, we use superconducting sensors to read out that energy. So and the performance of these sensors improves as their TC is actually lower. So we have to build an experiment that can take several kilograms of detector target material, as well as all the associated copper and sort of infrastructure around it, and cool it down to tens of millikelvin underground. So it is a challenge. Sure. But the upside of doing all this is it gives you access to dark matter candidates at a very large scale. So originally, the experiment, or the field as a whole, was designed to search for dark matter candidates on the order of GeV and above. And this NR means nuclear recoil. You're looking for models in which the dark matter particle is interacting primarily with the nucleus. There are ways you can, with doing clever data analysis, kind of extend the reach in mass a little bit lower. So you give up a little bit on your rejections, your background rejection sensitivity, but you extend it down to maybe a factor of a few more in mass, but not much lower. The technique of amplifying the signal by applying a high voltage allows you effectively to lower your energy threshold and search for dark matter particles below a GeV. And this works down to sort of something on the order of 100 MeV or so scale. Below that, you have to actually switch gear altogether. Heavy particles are predominantly expected to interact with the nucleus. However, there is nothing that says a dark matter particle cannot, or whatever that force, that interaction is, cannot interact with electrons at all. It just kinematically turns out that really you're gonna get a better likelihood for interacting with the electrons if your incoming candidate is in that lower, smaller mass scale, is on the order of mass scale of electrons. And so down below a GeV or 0.1 GeV to sort of from the order of 1 MeV. What these detectors are really sensitive to is a class of particles that would interact with the electrons of the atom rather than the nuclei. And then below that, you'd be sensitive to another class of particles that interact in a very different way, kind of like absorbing a photon. This would be a dark matter particle rather than an elastic scattering interaction, which I talked to you about. It's a totally inelastic scattering. It'd be absorbed by the electron in your atom, you eject it, and then you kind of observe the ejected electron after that. But this gives us a mass scale of, running from the 1 EV scale to 1 TeV, 12 orders of magnitude that you can potentially be sensitive to with these type of devices. And so actually I'm gonna skip this a bit and show you what the experiment looks like before. So the experiment is called SuperCDMS because it is the follow-up to the original experiment, which was called CDMS, cryogenic dark matter search. And we couldn't come up with a clever name for generation 2, so we just stuck super in front of it. Physicists are good at many things, but naming is not one of them. It depends on who you talk to if this is an impressive number or not. So it's in some areas of physics, we're 130 scientists from about 30 institutions across the country. Compared to collider experiments, this is peanuts, this is tiny. Compared to small sort of condensed matter type physics, this is huge. Compared to, space-based physics, this might be sort of something in the ballpark. But we have people mostly in the US and Canada, but also collaborators in Europe and India involved in this experiment. Last year, I showed this picture, is we had a collaboration meeting here in Florida. And for whatever reason, I managed to convince 100 people, well, not 100, we had about 50 people come down to Gainesville in August. Why they agreed to come in August, I don't know, but here's the proof. So where is this experiment going to be? I sort of was making the point earlier that you have to be underground to get away from sort of cosmic ray flux, the radioactivity. And it turns out there is a location in Canada and basically that is being built into a national lab in Sudbury, Canada. So this is way North Canada. There used to be a neutrino oscillation search experiment there called SNO. So the lab itself is called SNOLAB. It is part of an operating mine. So they're off there somewhere digging away for nickel, but there's a physics lab right up to the site. It is 2 kilometers deep. So you go in, you ride basically a cage down for takes you 5 minutes to get from the surface down to that level. You walk for 15-20 minutes. The resolution here is not good, but you're walking in a, basically a dirty mine. And then you come to a door and all of a sudden you transition from a dirty, dusty, messy mine into a clean room area that, it's a low sort of low background rare event search thing. So 2 kilometers deep, this gives you an equivalent amount of the number you want to compare it with, because rocks and earth kind of varies in composition to water. So it's the equivalent of having 6 kilometers of water above you. And it is operated, the entire lab here is operated as a clean room. For those of you who might have worked in a clean room, it's a class 2000, and it's a ginormous facility. So it is impressive that they can do that. So here is where we are building this experiment. I would say one of the also challenges in working, not that working underground is easy by any means, but it is an operating mine, and with mines, you have explosions, earthquakes, fires, stuff that happens that's par for the course for them. But if you're trying to build a sensitive instrument, finding ways to deal with that, when again, the spontaneous earthquakes are not something you can schedule and work your way around with. You have to deal with. The experiment itself this is one area of the lab. You can see kind of the hallways. It's going to be sited in this one corner. So in this green cylinder, the cylinder itself is shielding materials. It's polyethylene. It's meant to attenuate neutrons, and there's also some copper and lead meant to attenuate gamma rays. inside of that, you have a cryostat. And the cryostat consists of shells of, copper shells that take you from room temperature down to liquid nitrogen, liquid helium, and ultimately sort of the dilution refrigerator temperatures of 15 millikelvin. And the detectors go inside of that. So inside of here, you have the innermost region is the sort of 10 millikelvin region, and you insert the detectors there. They look like this. So I showed you the picture earlier. They're built into hexagonal housing, so we can stack them up together into a unit that's called a tower. And then we can arrange the towers in here, close everything up, cool it down to 10, 15 millikelvin and operate. So this is what it will look like inside. I mean, just simply getting this to work. And by the way, we are in the process of a lot of the stuff that you see in the picture is installed. We're actually right now about to get this thing underground and installed in the next few months. So this kind of sets the scale of where the experiment is. And this is a feat of engineering. I don't want to, I mean, I'm not necessarily involved in the details of this, but this goes beyond just physics stuff. You need thermal engineers, mechanical engineers, electrical engineers to make sure everything here works, not just at room temperature, but when you cool everything down, stuff moves. And you want to make sure it's still working at base temperature. Fairly challenging.
What's the physical size of that?
The innermost can is about this big. So it's on the order of, the volume is several cubic feet. By the time you get from the innermost can to the outermost can, it's a couple of meters in diameter. Yeah.
So roughly half a meter by half a meter size will be cooled at 15 millikelvins.
Yes. Yeah, so the detectors themselves are 30 kilograms in mass. I think the copper shell is probably something comparable to that. So, you're cooling something on the order of 50 to 100 kilograms down to 10 millikelvin. And we want it to stay cold for several years, it's the lifetime of the experiment. So this here, you can see sort of pictures. This is a picture of the detector tower. So I mean, everything looks like shiny copper on the outside, but each layer here is a detector, and sort of you can see the wiring coming down. This is the dilution refrigerator that was installed, delivered last year. So dilution, it's one of the three technologies we have that are able to cool us down to 10 millikelvin. And so this is a fairly large one as these things go, because it does have to cool that big mass.
How much is the temperature change due to the phonons created by dark matter?
Well, the temperature in the TES, in the sensor itself, is on the order of a fraction of a millikelvin.
So this 15 millikelvin has to be maintained much lower than fraction of a millikelvin. Is that correct?
Not quite, because there is a little bit of thermal. So you have, if you can think of it as an equivalent of an electric circuit, you have sort of the ground level is your 15 millikelvin. Then you have some thermal resistance, which is all the clamp that connects you. Then you have your crystal, which is a relatively large heat capacity, but that's also going to be close to 15 millikelvin. And then you have the sensor that is attached to the crystal. And so the phonons, the system is designed so that all of the energy of the phonons will end up in the TES rather than go out through the clamps and connections. And if you do it that way, you're changing the temperature of the TES by, let's say, half a millikelvin. You are sensitive to the actual base temperature, or to the ground a bit, but not quite as much as one might think. So if we went from 15 millikelvin to 16 or 17, we would start to see it in the pulses. The response changes, but it's not like a binary. It'll stop working altogether kind of thing. Yeah, that's why when we take data, one of the main variables you take is your fridge temperature, and you're always correcting your detector response against any drifts in time in your fridge temperature. You can see here, actually, we're building, so this dilution refrigerator is actually all the way back here. And this is the pad on which the cryostat is going to sit. And you can see the white discs are polyethylene shielding, and sort of there's a gray layer here that's lead shielding. And so that's going to build that the green cylinder I showed you in the previous slide, all the shielding that's going to surround the detector. The actual experiment itself is going to consist of 4 of these towers, so a total of 24 detectors that are made out of sort of a mixture of germanium and silicon. And the ultimate reach of these, so this is the same plot that I showed you earlier. This is the projected reach of this experiment. Kind of, if you look at the combined lower line, it shows you the cross section that we'll be able to get to. And in this version of the experiment, we're gonna it'll get close to where neutrinos are going to become a serious issue. As I said, we actually do expect to see on the order of tens of neutrinos in the experiment. And to go beyond that, it'll start becoming a challenge. Yeah, skip that. So anyways, so this is where we are. The experiment itself, its goal is to get down to the neutrino region in the sort of 1 to 10 GeV scale, but the detectors themselves, the way you analyze the data, I mean, you turn them on and you run. So it's not like there's different modes of operating, but you can do specific analyses to look for sort of the heavy dark matter candidates or sort of the MEV or EV dark matter candidates. So this is all looking at the same data and analyzing it. The experiment itself, as I mentioned, is being installed right now, and hopefully, fingers crossed, it will be done in sort of early mid 2025. So, and 1 more year. At that point, we'll be ready to turn the devices on, start commissioning, start taking data. There's a facility actually right next to it that is also a dilution refrigerator. We're running 6 of the detectors in there right now, and this is our first look at how these guys are working underground and kind of give us a clue of how things will be when we're up and running with the full experiment. So this kind of brings me to the end of the talk, and something I like to conclude with is that I showed you early on that, like, the ginormous plot and log space mass cross section where dark matter can be. It's really a needle in a haystack. But there's a history of sort of major physics discoveries that from the time the idea was postulated to the time they were detected, it spans decades. I mean, neutrinos are really the original sort of dark matter, right? There was good reason to think something was out there. There had to be a new particle, and it took 30 years, which may have sounded long at the time, but then kind of, if you look at the history between when the Higgs boson was first postulated and discovered 50 years, gravitational waves is even longer. So that's been around since GR came around. And dark matter, I'm hoping it does not run more than 100 years, but this is right now the big unknown, because again, the point I want to make is we have very good reason, very good understanding based on astrophysics, based on observing how things are moving out there, to think that there has to be a different kind of particle out there. A particle, as we understand, sort of something gravitationally attractive. But we don't really know much else. It's not as constrained. So we're looking in one place. We're hoping it's there nearby, but it's, yeah, when we actually discover it, I'm not even willing to narrow it down to after the century. But I'll stop here. This is my document.
Thank you. Any questions?
I do have.
Yeah, go ahead.
Okay. I mean, this might be very like, I don't know, but I was wondering, is there like 2 ideas, or does everybody agrees in that it has to be dark matter, or are there another like different idea of being, I don't know, like a different region of in the law of the gravitational or general relativity, of how works,
Right.
how gravity works in, I can think this.
Yeah, so absolutely not everyone agrees, and people are seriously examining, okay, what else is out there? So, you're coming out with a claim saying, I need something brand new, or some bit of physics that's brand new, or why does it have to be a brand new particle? Why can't it be different gravity? And the rotation curves are actually one such example where there are people who have worked out a variance of general relativity where gravity falls off as with lower acceleration. So it's not just proportional to mass, it's proportional to acceleration. And so it falls off in a different way and produces the same Earth. So how do you pick from one versus the other? From an experimental point of view, it's okay, you don't know, you have to go out and measure it. I think what gives dark matter the edge in terms of the most likely explanation is it satisfies a set of very different observations. So modifying gravity, you can do that to explain galactic rotation curves. It works at that scale. But it doesn't explain things that observations from galactic lensing, or doesn't explain observations from supernova, or observations of the element abundance. All of those different things are saying, all of these can be explained by saying there's a dark matter particle, but other explanations might be able to explain one or two. And that's not to say at the end of the day, maybe one of these theories will turn out, they'll figure it out. But right now, the community is still thinking dark matter is as far out as it seems, it's the most, it's the least far-fetched explanation, is what I'm trying to say. And mathematically, it's understood, like we know what to predict and calculate, and you can look for it, and it's falsifiable in that sense.
Okay, so suppose the dark matter particles are lower mass, like mega electron volts. How do you build a detector for that? What do you look for? What principles would be useful?
Well, so yeah, it very much depends on the mass, like I said. So if the dark matter particle is GeV, sort of proton and nucleon scale, the most likely interaction is with the nucleus, which is fine. If you go down to MeV, then you kinematically it's better matched with electrons. But the good thing is whatever detector you build that'll have nuclei will also have electrons. So in a sense, in that plot that I showed you with the mass range, that the same detectors are also sensitive to MeV scale particles. Again, you have to do your analysis a little bit differently, but the technique is the same. If you go below 1 eV, however, at least our detectors can't work anymore, because now you're lower than the energy of the gap in silicon, and you're not going to get much of you're not going to be able to create electron hole pairs. But if you go even lower, so there's no reason, by the way, to stop at EV. There's a class of dark matter particles called axions that come from a different part of particle theory, but those are micro EV or nano EV in mass. At that point, these particles are behaving more like EM waves. And you search for them in a totally different way, with things like effectively, they're called resonator cavities. You're building like super sensitive antennas that can look for energy in particular frequency rather than looking for discrete particle interactions. So yes, the technique you use really depends on the mass type of candidate. We are lucky in the sense that GeV and MeV and a little bit less, we can look for it with the same device.
Okay, any other questions?
When you reach the neutrino limit, you can actually say about the neutrino flux, right?
Yes. So
what energy range that will be?
So there are two main features to the neutrino flux. There's solar neutrinos, and those are the lower energy range. Those look a lot like sort of the few GeV dark matter candidates. And then there's atmospheric neutrinos, and those are much higher in energy, and those sort of look like sort of the really GeV, the 10 GeV, 100 GeV type of dark matter candidates. There was an excitement in the field is once you're able, so the atmospheric neutrinos are more of a nuisance than anything else because they're there's not much we can do with them. But if you see solar neutrinos, there was an open question in physics and neutrino physics about possibility of observing something called coherent neutrino interactions. Which hasn't been observed before. Actually, it ended up being observed in a reactor-based experiment only a couple of years ago. But the dark matter experiments observing it from solar neutrinos can add more to that study. So in a sense, we can become neutrino physicists all of a sudden. that there is, in a sense, something to look for in those solar neutrinos. However, so the thing with neutrinos, I said before, is you can calculate what that spectrum looks like. And the more you know about it, the more you can calculate theoretically and predict its shape, the less of a problem it becomes. Because, if the spectrum looks exactly like this and nothing else, then it's easy to distinguish from dark matter. It's only the uncertainty that makes it an issue. And so what I think will happen as sort of years pass by, you get better measurements of the solar neutrino flux, better calculations of what it should be, and then you'll see that the neutrino barrier will sort of slowly kind of fade down as the uncertainty decreases.
Okay,
Sorry.
I'm sorry, go
You
ahead.
said neutrino. So, is there a possibility to detect any supernova explosion and things like that?
No, unfortunately not. Our mass of tens or hundreds of kilograms compared to sort of the large neutrino experiments, which are, thousands and thousands of kilograms. If they see a handful of neutrinos, we're gonna see maybe 1% of a neutrino. So we're not gonna see neutrinos, supernovas that way. But just the flux from the sun is continuous and large enough that, yeah, we'll get some.
Thank you.
All right, any other questions from the online participants? We have no more questions. Let's thank our speaker again.
Thanks, and again, I do appreciate the chance to come down.